Thank you very much for the invitation and the introduction. It is certainly a tremendous honor to speak here and to kick off Jim's birthday conference. I'm going to be speaking about the unitary dual. And before I begin, just a couple of comments. I want to encourage people to ask questions. And somebody said something about the mic, but if you just want to ask a question, I can repeat it into the microphone. And I want to encourage people to ask questions because I can't possibly get through all my slides anyway, so you might as well ask me. And I also want to just mention up front that one of the topics of this talk, or behind the scenes a little bit, is the Atlas software, which many of you have heard about. And almost everybody in this room has heard me make this pitch before, but I like to make it always, which is that we love doing examples with the Atlas software. So if you have something you think, a computation that you think might be interesting that we could do, please come see me or one of the other Atlas people here. We love it for several reasons. One is it helps us test the software. Another is virtually every time somebody asks me an example, I learn something. And of course, it's nice to provide a service. So the Atlas project is a long-running project, and there have been quite a few people involved with it over the years. And here's the list, and the names in brown are the names in black are the people that are still actively involved. I'm going to give the big picture, which is the setting is a connected complex reductive group defined over R, and the problem is to describe or compute or understand, I'm not sure which word to use, the unitary dual of G of R. That is to say, the collection of irreducible unitary representations modulo the appropriate notion of equivalence. Okay, I'm going to make an assumption right from the beginning, and that is that you believe this is an interesting question, and I don't need to say any more about that. If you don't think it's interesting, I suspect you wouldn't be here. So as you all know, Weil sort of kicked this off in the 20s with compact groups, and SL2 was done in 1947 by Bargmann, and since then there have been many, many results. I'm not going to list any one of them, just to say that it's well known that this is a very hard problem and that the answer is very complicated. And in 2002, we had the idea of trying to use a computer to study this problem. And I'll just say now that if I'd known, well, in 2002, I think my guess is that it would either take us 10 years or we'd never do it. And the fact that it took us 23 years and we did it is very surprising to me. So today I'm going to report on an algorithm to compute the unitary dual and say a few words about the actual computations, and parallel to that, in progress on this conceptual understanding of the unitary dual. These two go hand in hand. And that is basically saying that I'm going to talk about Arthur's conjectures and beyond. Okay, so here's a picture of how I view the subject. We're interested in the unitary dual. And in my mind, what's happened is quite marvelous in that there were three major strands that came together to prove the unitary dual. And I'm going to illustrate them here. One is, I call it Vogin theory, which is shorthand for all of David Vogin's papers plus other people, and then the Atlas software. There's Arthur's conjectures, and there's Hodge theory as envisioned by Wilfried Schmidt and Kari Valonen. And these things are all intimately related. There are all sorts of relations between these threads. The first one I'll mention is going from Vogin theory to Arthur's conjectures. I refer there to Barbash and Vogin. And if you read Jim's 1981 paper, where he spelled out his conjectures, one of the things he says he was motivated by trying to understand the unipotent representations that Barbash and Vogin had discovered. And I'll say the difference between Jim and the rest of us is that we all were trying to understand Barbash and Vogin's construction, but we just kind of scratched our heads, and Jim came up with this incredible theory to explain it. And then, of course, going the other way, his conjectures have been a major source of inspiration for our project. There's a map going from Atlas to Hodge theory. I'm going to talk a little bit more about this. But I put down two things here, the invention of the C form and a computation that we did, which was critical for Schmidt and Vallonen's understanding of Hodge theory. But once they did that, there's tremendous information going back the other way, in particular, a proof of the FPP conjecture, which I'm going to talk about due to Davis and Mason Brown. And then in the same sort of sphere, there's maps from Hodge theory to Arthur's conjectures. So all of these things, they all work together. Okay, so I hope everybody's had their coffee. We're going to hit the ground running here. I'm going to explain in an hour what I've been doing for the last 23 years. One of the things that I think has happened, I believe, maybe you'll tell me at the end of the hour, is after thinking about this stuff for so long, I actually think I've gotten my brain around it and I can explain the whole picture in an hour, which definitely didn't used to be the case. So let's see. So we're going to talk about GK modules, and we're going to use the Cartan classification of real forms in terms of an algebraic involution theta. So forget about sigma and anti-holomorphic involution for a long time. K is the fixed points of G, and K of R is a maximal compact subgroup of G. And we're given a vector space with compatible actions of G and K. That's what a GK module is. And once and for all, we're going to fix a Cartan subgroup H of our complex group with Lie algebra H. And this is a little bit of a point of view picture. You think of like real groups or p-adic groups have lots of different Cartan subgroups. Well, there's really only one, and fix it from the get-go. And an element of H star defines an infinitesimal character. And you have the Grothendieck group of virtual characters with infinitesimal character gamma. So that's finite sums of irreducible representations with infinitesimal character gamma. And so this is a Z module, finite dimensional, and it's spanned, well, it's spanned by irreducibles by definition, and by a theorem of Zuckerman, it also has a basis in terms of standard modules. I'm only going to say this once. Everywhere, we're only talking about real infinitesimal character. There's a reduction from all infinitesimal characters to real, which I'm going to ignore. So Langlands, together with Knapp, Vogel, and Zuckerman, gave an explicit description of the admissible dual, that is to say, the irreducible admissible representations. And so they described a parameterization, which we implemented. One of the first things we did in the Atlas project was implemented a version of that. So we have a set of parameters we call P sub gamma. It's a set of parameters for the irreducible or standard modules in M gamma. And I'll say a few words about that. Gamma is a triple, X lambda and nu. X is an element, it's a K orbit on G mod B. So geometrically, this is a very natural object. That's a finite set. And so we explicitly compute it, and we just write it as a finite set x0 through xn. And then given X, you're handed a Borel subalgebra. Well, that's what it means to be an element of K orbit on G mod B. It's a K conjugacy class of Borels. And so you have a Borel subalgebra containing H. And you also are handed an involution theta sub X of H. And then you're also handed the next piece of data is lambda, which is an element of X upper star. That's the algebraic characters of X upper star. So that's a lattice. It's shifted by rho. And that gives you a character of the H of R upper theta X. That's the maximal compact subgroup of H of R. And then there's the rho cover, which you can ignore most of the time. And you're also going to be given an element, excuse me, of the rational, the X upper star tensored with Q, and that corresponds to having a character of the minus theta part of the Lie algebra. So the summary of all of this is that gamma is, you just think of it as three pieces of data. It's a finite set, a vector, an n vector where n is the rank, and a rational vector of the same size. And that vector is, there's really a plus rho, but never mind. Though that's the kind of data that parameterizes a representation. And altogether, those things give you a character of this real Cartan subgroup. First of all, they give you a real version of the Cartan from theta and a character of it. And roughly speaking, that's what you need to make a representation. So here's how that works. Given a gamma, you get this collection of parameters, and for each parameter, you get a standard module. And a standard module is induced from a limit of discrete series on a real Levy factor. And each standard module has a unique irreducible quotient. And the theorem of Langlands and Zuckerman and Vogel is that the admissible dual, the irreducible admissible representations are precisely these representations J of gamma, where gamma runs over H star modulo W, that's the infinitesimal characters. And for each gamma, little gamma, capital gamma is an element of this explicit set. And from what I said before, this Grothendieck group has two bases, the I gammas and the J gammas. So there's a change of basis between them, and that's the famous Kazhdan-Lustig-Vogel polynomials. So I'm writing those as P and Q. So these are polynomials in an indeterminate Q. And the theorem says that you can write an irreducible, you can write a standard module as a sum of irreducibles. And you can also write an irreducible module as a sum of standards. And the coefficients are given by these polynomials P and Q, which are up to the sign inverse matrices of each other. So these are extremely interesting, difficult to compute. They contain a lot of geometry in them. And that's kind of the DNA of everything we do. Okay, so we're talking about unitary representations, which has something to do with Hermitian forms. So in the language of GK modules, here's what that looks like. We don't have a Hilbert space here. We have just an algebraic vector space. To say you have an invariant Hermitian form on it is to say you have a Hermitian form on the vector space with this invariance property. That's the standard invariance that you ask for. And there's also a corresponding relationship for the action of K. Well, one of the principles is that you should never talk about the real Lie algebra. Everything's complex. So if you want to state things in terms of the complex algebra, you it just occurred to me, I'm not going to use this, but is there a laser? No. Okay, never mind. Well, I'm standing right here. This you put this anti-holomorphic involution sigma here, and that's what you have to do for this to be make sense. And the Hermitian dual, that is to say representations admitting an invariant Hermitian form, is known by a theorem of Knapp and Zuckerman. So we have the following picture. There are these various classes of representations. There's the discrete series, the tempered representations, the unitary representations, Hermitian and admissible. And everything in this picture is known except the unitary set. So the problem is to describe this set in between here and here. So that gives a restatement of the problem. If you give me a representation which has an invariant Hermitian form, just determine if the form is positive definite or not. Excuse me. And secondly, for a given group, somehow describe all of them. Well, okay, the first step alone seems pretty difficult. How do you compute the signature of a Hermitian form on an infinite dimensional vector space? Well, in general, that might seem like an infinite calculation, but there's lots of structure here. And so this goes back to Vogel's work in the 80s, stated in terms of our parameterization. We have a parameter x lambda nu and a standard module. And this nu is an element of a real or rational vector space. So you can deform it continuously. Lambda is an element of a lattice, that's rigid, but nu can be deformed. And just think principal series, nu is like the character of A. So you can deform nu to 0. And this family of representations have, assuming they have an invariant Hermitian form, the form depends on nu and it's upper semi-continuous. So it can jump, but only at a finite number of points, and at a finite number of points, the change in sign is can be computed. And what happens is at a reducibility point, the sign can change at odd levels of the Janssen filtration. And that's computed by the KLV polynomials. So in principle, we should be able to do the following. To compute the form, the Hermitian form on a standard module, by induction, deform it to 0. At 0, it's unitary, so you know it's positive definite there. And then just keep track of the sign changes as you go. Well, this was David's, David and other people spent a lot of time trying to do this in the 80s, and they made substantial progress, but there's a major fly in this ointment, which is that, well, first of all, the standard module might not have an invariant Hermitian form. That might not seem so serious, but it is. Anyway, that's a problem. And secondly, even if it does, it's not canonical. And if you don't believe me, look at SL2R, look at an odd principal series of SL2R with real new parameter, odd meaning odd K-types. And if you just write down a simple formula, you see it has two lowest K-types, plus or minus 1, and any invariant form has to have opposite signs on them. So there's no way to make it canonical. And this is where we were stuck for a long, long time. It's great. You can say let's implement and let's formulate an algorithm, but without canonical things, you're lost. Well, okay. So remember the Hermitian form. I put back up here the definition. It's this formula here, where sigma is the anti-holomorphic involution defining G. And we had the idea to modify this and use sigma C instead. So for every group, there's a canonical compact form of that group. That's something special about real groups. I don't know what to do in the p-adic case, but there's a compact form. So you can take sigma C to be the anti-holomorphic involution, which defines the compact one. And you can modify this definition using sigma C instead. Now, I just played a little trick there. It's a little hard to see, so I'll go back. The only thing I did in that formula was I inserted that C, the red sigma C there. That's the only, sorry. That's the only difference, and I put a C subscript on those. So it's the same formula, but with this other anti-holomorphic involution. What? When I first saw this, that's what I said. How can this mean anything? Sigma C has nothing to do with C. This isn't an invariant Hermitian form on the representation. What is it? It's not something that seems natural. And well, it does make sense if you just go through the formalities. Everything I said makes sense. This thing's well defined. And about 10 years ago, we proved the following theorem. Every irreducible representation admits a canonical invariant C form. So that it takes care of two things. They always exist and they're always canonical. And canonical is you make them positive on all of the lowest K types. And, excuse me, there's an algorithm to go from to relate the Hermitian form to the C form, to go back and forth. So of course, without two, you'd just be doing something formal and ridiculous and meaningless. But if you compute the C form, you can then use a formula to compute the honest Hermitian form. Okay, so that's where this real infinitesimal character comes in. If you strict the real infinitesimal character, then it always exists.
Sorry, I think the question was about number 2.
Is that the question?
No, it was about 1.
Oh, okay. Yeah, okay. So yeah, so 2 says if it exists, then there's an algorithm to compute it. Sure.
Is there something implicit in this? Is that you already know that you have to compute on a non-finite set of K-types?
That's an excellent question. So the question was, do we know that there's some computation that we need to do on a finite set of k-types. And in a sense, the answer is yes. In principle, there's a finite set of k-types where if you check that the form is positive definite on those, then it's positive definite. That set is huge and impractical, but we do have a finite calculation in the end. Okay, so write sub C to indicate we're equipping these forms with their C form. And now it's time for a digression. In the 1980s, Schmidt and Valonen observed that every representation has a canonical Hodge filtration. And the canonical there is hugely important. This is via Saito's theory of mixed Hodge modules. And they observed then that it's clearly related somehow to the Hermitian form. A filtration is it's a infinite sequence. It's graded by, it's a Z grading, and the Hermitian form is a Z2 grading, and somehow the signs that come up in Hodge theory look kind of like the signs that come up in computing Hermitian forms. Question?
Is it a mixed Hodge structure?
Yes.
And is it a rational Hodge structure or just a real Hodge structure? Rational
This is a subtle point that I'm not qualified to speak precisely on, but
there's not a rational structure on it. It's just a real structure.
yes, I think so. My understanding is that it's a real structure, and a lot of the theorems are only about rational, and Schmidt and Valonen were careful at some point to say that you can go from one to the other.
And so this is related. You don't assume integrity or anything on the.
No, certainly not. Certainly not. No, so the question was integral infinitesimal character, and the answer is no. Well, they observed that it's clearly somehow related to the signs of the Hermitian form, but one is canonical and the other isn't. So you know that there's trouble. And well, that's where the canonical C form comes in. They realized that that was the missing piece. And in 2011, they modified their conjecture to state that there's a precise relationship between the Hodge filtration and the canonical C form. And that's a beautiful conjecture, and everything's canonical on both sides. And but it's a very, very difficult conjecture. And based on some conjectures about the Hodge filtration from talking to Kari and friends, we knew some basic properties that the Hodge filtration was supposed to satisfy. If you assume those, you can formulate an algorithm to compute the Hodge filtration, basically by taking the algorithm that we had for computing the C form and modifying it appropriately. And so we did that and implemented it in Atlas. And once we'd done that, Kari and Dougal Davis were able to go back and use that to prove a slightly weak version of their conjecture. So the full strength of their conjecture still hasn't been proved, and I don't know if it ever will be, but what they've proved is more than enough for applications to representation theory. And basically, it's what I said earlier, the Hodge filtration, which is a Z object, if you reduce it mod 2, you get the Hermitian form filtration, the Z2 grading of the Hermitian form. Okay, so back to our regularly scheduled program. We need to look at restricting to K. A representation restricting to K has a formula like this. We need to parameterize K, and well, K could be disconnected, so you can't exactly use the theory of highest weights. We define a temperic representation to be one which is tempered and has real infinitesimal character. And in terms of the x lambda nu parameters, tempered means lambda, nu is real, and tempered means nu is purely imaginary, and real means real. So the intersection of those two is simply you're saying nu is equal to 0, which we've seen these guys came up earlier. That's precisely these representations. And David proved, first of all, that the temperic representations are in bijection with K hat, where you take a representation to its lowest K type. And if you have any representation, you can find a formula for its restriction to K as a finite sum of temperic representations. I didn't write that on the right-hand side. It's a finite sum, and these guys are temperic. And so this is where the finiteness comes in that you were asking about. Okay, so we take this ring Z bracket S, and we use this to encode a representation with a form on the K-type. A plus BS times mu means you have A copies of mu with the positive form, A copies of the positive form, and B copies of the negative one. So that keeps track of signs. And Vogin proved that there's a unique formula that if you, on the left-hand side, I should have the form. Yeah, on the left-hand side, I should have the form on this representation has an expression like this. This is a refinement of the previous statement. You can also keep track of the forms by putting these coefficients in. And so now we can reformulate David's algorithm as follows. You start with a standard module and deform it to 0 and keep track of the form along the way. Each step of the way, you get some other terms which are in some sense smaller parameters, and you get an extremely complicated inductive algorithm. And I'll show you the main step of the algorithm. If you have a standard module given by x lambda t nu, and think of t as varying, the algorithm, the main step in the algorithm is the following. Suppose at t, the representation is reducible. So this is relating the form on the representation just above t to the form just below t. So that is to say, as you deform through t, there's some changes in sign. And the changes in sign are kept track of by this thing. Now, I'm not going to try and parse this, but just point out that it's a finite sum, and it involves the Kazhdan-Lusztig polynomials. So
You left out the equal.
no, that's the L naughts. I wasn't going to mention them. So by induction, so this last right here, yeah. So this is the C form on a temperic representation. So this whole formula is saying, oh, sorry, not on temperic. Yeah, well, it's a K-type, except that we're representing K-types by standard modules restricted to K. So as our basis of K hat, that's what we're using. And then in that sense, that's what it is. Well, there's not so much content to it, just that, I mean, there's, yeah, so that's the point. So that there's a formula like this if you put irreducibles of K here, but instead you can use temperic representations, infinite dimensional representations restricted to K. That's also a basis. Sorry, what's explicit? N. Oh, yeah, everything. So the question is about N being explicit. Or in the previous slide. Well, yes. I mean, here it is. That's a formula.
Actually, in this formula, nothing is temperic.
No, this is just the one step. This is a standard module with a smaller nu. And this is an inductive algorithm, so you have to repeat that, and eventually you get to nu is 0. Okay. So eventually you get a formula like this. The C form on a standard module is a linear combination of C forms on temperic representations with some coefficients. That's at the end of this long algorithm. And I'll remind you that there's a formula for writing an irreducible as a sum of standards, and there's a misprint here. You know, how many, you can read the slides over 100 times. That's supposed to be a standard module. And you can refine this formula to actually give a formula for the C form. And amazingly, it's almost the same formula where you just plug in S here instead of 1. So if you put all of that together, the conclusion is that we've sketched an algorithm to write an irreducible as a linear combination, an irreducible now, not a standard, as a linear combination of temperic representations with some coefficients. Now, trust me, that's a very long algorithm, and you can't do it by hand. Remember, on the right-hand side, they're temperic, so they're unitary. So you can convert this formula to remove the C's. That's a formula for the C forms. This is a formula for the emission forms with some different coefficients. And now, according to David's theorem, the representation is unitary if and only if all of those coefficients have 0 S term, because the S term is telling you about the minus part. Yes, that's an interesting question. So in some sense, that's answered by the first point on this slide, which is that at some point, at the very end, the whole program just has to do with the C form. The very last step, you have to convert to the ordinary form. There's a choice. So you could get plus or minus. But in terms of being positive definite, it doesn't matter. No, there's a uniform choice for all of them. There's a single, you need to choose a single root of unity. Amazingly enough. It's a good question. Oh, sorry, for people who couldn't hear, maybe I should have repeated the question. The question was, didn't you say that the Hermitian form is not canonical? And I did say that, but it doesn't matter.
With the nu is 0 in the formula for J of gamma, and so that standard module has a unique lowest K type, which means it has a canonical Hermitian form that's positive on that lowest K type.
All right, so I said ignore this slide, and I'm going to do that because I'm running late. I'll just mention in the unequal rank case, there's a huge, long, interesting, complicated digression about twisted KLV polynomials, which I'm entirely ignoring. Okay, so the conclusion from all of this is we have an algorithm to compute if a single representation is unitary. Now, what about the entire unitary dual? That's a different question. So the canonical example to have in your brain is the spherical unitary dual of G2. Gamma, the representations here, they all have the same x and rho. X is the open orbit and rho is rho. And nu is an element of R2. And here's a famous picture from David's paper in the 80s about the unitary dual of G2. So this is a family of nus, and the ones in red are precisely the unitary ones. And excuse me, this picture illustrates the main idea, which is that there's a facet decomposition of this space, and the lines are reducibility points, and unitarity can only change at a reducibility point. So that is to say, if you compute a point in one of these open triangles and it's unitary, then the whole triangle is unitary. So there's essentially a finite number of points. Well, in a bounded region, there's a finite number of regions. So the fundamental parallelepiped, and I checked the spelling of the word, is the following set. Whoops. It's the set of elements in the real span of the roots, the real span of the roots, for which all of the simple co-roots are between 0 and 1. And I have some models here, which I had to bring. Which one should I show? This is the fundamental parallelepiped for C3. And if besides the picture that I showed, the slide I showed earlier with the unitary dual, if you get anything else out of this talk, please come up and admire these. They're fascinating to look at. Anyway, those are the fundamental parallelepipeds. These are these finite regions. It's a finite union of facets of dimension 0 up to the rank. And it's the size of it is it's the closure of the union of the number of orbits, the number of alcoves, a number of copies of the alcove, the fundamental alcove, and the number is the cardinality of the Weyl group divided by the order of the center. And so if you have a representation, its infinitesimal character is given by this formula. And so by definition, the FPP unitary dual is a set of irreducible unitary representations where the infinitesimal character is in the FPP. So in the case of G2, in the case of spherical, it's a very familiar picture. We're basically generalizing these pictures for spherical representations, which are well known for both real and p-adic groups. If you're up on the split carton, that's the picture. If you're on a less split carton, the pictures are sort of the same, except that everything's going on in the -1 eigenspace of theta. So these vector spaces are getting smaller and smaller all the way down to the discrete series where they're just points. But that's the picture. And it's sort of amazing to me that that's how it works, that the spherical case generalizes rather simply. And there's a beautiful theorem by Dougal-David, a conjecture by David. I'm going to state the conjecture in stating the theorem, which is proved by Dougal-Davis and Lucas Mason-Brown. If you have an irreducible representation whose infinitesimal character is not in the FPP, then there's a theta stable parabolic, Q equals LU, and an irreducible representation of L, and they're both given explicitly, such that pi is obtained on the nose by cohomological induction from pi sub L, and unitarity is preserved. So pi is unitary if and only if pi L is unitary, and you've reduced the problem to a smaller group. And this induction is for the experts, is in the weakly fair range, which is why 2 holds. Weakly good range. Thank you. Okay. So, did I not say that? Sorry, that's a good point. Important point. Sorry. This irreducible is in the FPP for L. I forgot to say that. Thank you. The set of pairs x lambda, such that there exists a nu in the FPP, is a finite set, and this facet decomposition for a given x lambda is finite, and unitarity is constant on facets. And so you put all of that together, and calculating the FPP unitary dual is a finite problem. You have a finite number of x lambdas to run over, and for each of those, a finite number of facets to check. And together with the reduction, you get a description of the unitary dual. So let me take a digression here to talk a little bit about the topology. The unitary dual is a closed set in the Feld topology. And so these facets have a natural topology. And it's just back to the G2 picture. It's sort of what I was saying before. The unitary set is closed in the standard topology. So if a point in a triangle is unitary, then the closure of that triangle is unitary. So for example, this is the trivial representation. That gives you a non-unitarity result. It says that the representations of this triangle or this line are not unitary. Oh, sorry. No, I said that wrong, didn't I? Sorry, never mind. There's a lot of information in the closure relations. But just a word of caution, the topology on the spherical set, it's not isolated. It's not separate from the rest of the unitary dual. It's a big complicated thing. So how this all fits together is extremely interesting. So here's a picture for E8. E8 split has 9,282 unitary spherical representations. Sorry, what?
Before you go on about this, so first of all, as you can see on David's paper in Smart City 2004, the problem is that the first topology is perfectly clear on the unitary dual, but it has never been completely written for the admissible dual. So that's your reference.
That I hadn't thought about that, so I plead ignorance. So the question was, sorry for people who didn't hear, The Fell topology is perfectly well defined on the unitary dual, but it hasn't been carefully written down on the admissible dual. And
Am I right?
I think you're probably right.
I think he's making a, I think he's saying if you intersect, look at the unitary dual for a fixed x and lambda, the topology agrees with the Euclidean topology in the news case.
Of the data.
Yeah.
Yes. But again, this could have to be. And the second thing is, as you said, if you have, for example, one spherical sheet and one non-spherical sheet, things will interact mysteriously, right? Do you understand this?
no.
Okay.
The question was that different series for different x lambdas can interact with each other. And do I understand that? And the answer was no.
There's no problem with defining a Fell topology on the admissible dual in the case of reductive groups. You just want to talk about limits of matrix, or of K-finite matrix coefficients.
Just like the same definition.
Yes. Fell didn't care about K-finite, and didn't care about reductive, and very general thing, but it doesn't want a topology on fuzzy simple representations. And
Yeah, okay. So for the viewing audience, David Vogan just explained that for reductive groups, quasi-simple representations, you can use Fell's definition if you apply it to K-finite matrix coefficients, and then everything's fine for the admissible dual. So here's a picture. These are the 9,282 spherical unitary representations of E8 and their closure relations among them. So obviously there's a huge blob, which is hard to understand, but even the blob has some interesting structure in it. And then there are these other isolated pieces. And so here's a closer look at the isolated pieces. For example, that's the trivial representation, which is isolated in the spherical unitary dual. And I'll zoom in one more time. Excuse me. Right here, for example, so each of these points, it's labeled by its dimension. So this is a two-dimensional facet, and it has three one-dimensional things on the boundary and three zero-dimensional things on the boundary. So that's a triangle, and then that's a triangle, and this is two triangles attached at a point.
But Jeff, the labels seem to contain.
Well, in the case of a unipotent representation, there's a third entry which is telling you what unipotent representation it is. But most of these, it's just a number labeling the representation and a number giving the dimension. And so it's a beautiful picture. And okay, so let me summarize our description of the unitary dual. We have this set I call the G hat FPP, the unitary representations coming from the FPP. You take the collection of theta stable parabolics up to conjugation by K, and then the theorem is that the unitary dual is the union over all of the theta stable parabolics of the cohomological induction of these FPPs. So there's the base case, which is the FPP itself, and then all of the FPPs for the theta stable subalgebras. All right, I'm going to skip the next couple of slides. If you want to look, here's a slide of the times for all of the groups up to rank 6. And you'll notice they're all extremely fast. I'll just say a few words about E8. We've done E7 split many times, and it runs in about 16 hours on a laptop or about an hour on a parallel machine. And if somebody wants to talk to me about why that factor isn't a lot greater than 16, that's a very interesting topic. Steve Miller computed the FPP unitary set for E8 split. So in some sense, we're done. Well, if you consider E8 as being done. He did this over many months, sort of cranking through on a big computer. And the conclusion is that there are 3 million and such 3 million plus unitary representations in the FPP. It's an explicit list.
unitary faces.
Excuse me, sorry, good point. Unitary faces. So each face is a simplex of some dimension. All of those representations are unitary. We've checked in some sense independently that these are indeed unitary. The hard part is checking that all the remaining ones are not. If you look at some numbers, there are billions and billions of non-unitary representations and not many unitary ones. So the second, checking that you haven't missed anything is extremely hard. We haven't finished that, but in some sense, I have a lot of faith in this number. I would say there's a small possibility it'll get slightly larger, but I doubt it. So here are some numbers for E6, excuse me, E7, E8. And well, and I put a question mark here because it wasn't just a run, it was like months or a year and a half or something of piece by piece calculations. We do hope to be able to run it fairly quickly on a parallel machine. I should mention this 16 hours for E7. That's a very impressive number. When we first started, it was months or something, or years. And it's been a lot of hard work. David is basically, everything David knows about representation theory has gone into improving this algorithm. And a lot of things that he didn't know about it, which he learned in doing it. It's a very impressive algorithm. Okay, so let me wrap up and answer the following question, which I've been asked, but that's just the calculation. And I agree with that. We'd like a conceptual understanding. Well, that's basically Arthur's conjectures, and that's been proceeding on a parallel track. And I'll just say, if you have an Arthur parameter, attached to an Arthur parameter is an Arthur packet. And in our setting, I'm using the term to refer to the packets that were defined in my book with Barbash and Vogan, sometimes known as ABV packets. And by definition, these are unipotent if the parameter is trivial on the C-cross. And here's a theorem. If psi is unipotent, then every representation in that packet is unitary. And in general Arthur packets, many cases, all of the representations are known to be unitary. We're not quite done with all of the cases. And the history of this theorem is long and complicated. It has many contributors, and I'm not going to try and spell out everyone's contribution. It's impossible. And I apologize beforehand if I haven't correctly given credit to somebody. Real means not complex. Real groups and complex groups. So the sort of starting point of all of this is Jim's book. So I put his name in bold. And then there's a number of other results that go along with it, extending it to to quasi-split groups and relating Arthur packets and ABV packets and various things. And if you put that all together, you conclude that 1 and 2 are both true for real classical quasi-split groups. Barbash and Ma, Sun and Zhu have an independent program using the theta correspondence to prove 1 for all real classical groups, not just quasi-split, using the theta correspondence. Myself and these others, we computed by Atlas, by computer, we computed the unipotent representations for real exceptional groups a number of years ago. And now, fairly recently, Dougal, Davis, and Lucas Mason Brown have a uniform proof of a lot of this. First of all complex groups for part 1. All unipotent representations of complex groups are now known to be unitary. And this is an application of Hodge theory. And in an ongoing work, we were working on proving extending 1 to all cases, again, a uniform proof. And we know 2 under a certain genericity condition, but we're still struggling to close the gap. Okay, so I'll just conclude by saying, where are we now? What's left? Well, let's assume that we've proved all of Arthur's representations are unitary. What's missing? Well, it's well known that they're complementary series. And, that's one thing. It's also known that there are some quote unquote unipotent representations which are not in this list. For example, the oscillator representation is not unipotent by Arthur's definition. And you may object that the oscillator representation is a representation of a nonlinear group, but WeTech's going to address that later. And anyway, you can talk about the oscillator representation of sp2nc. So there's definitely, and way back in the 90s, when David wrote his orange book about unitary representations, there's a long discussion towards the end about the proper, what various generalized notions of unipotent representation should be. It's an extremely interesting topic. And there may still be some surprises, we're not sure. And so that's just an advertisement for the next talk. Wait, don't clap yet. And thank you, and thanks to Jim.